Hello everyone, I am Somesha Chanapati, Assistant Professor of Civil Engineering at Vedang Institute of Technology. Now we will solve one numerical while there is application of one UVL and you can see one point load is there. So if we follow our first step, let's calculate our reaction forces. Okay. So first step is calculation of reaction forces. So at point A, we know there will be generation of reaction RA and here we will have RB. So we know that summation of all the vertical forces will be 0. From this we can calculate that RA plus RB is equals to, okay, you can see this triangular force we will have in our previous numericals while we solve, we just need to calculate the area of the triangle. But here this 30 kilonewton is the area of the triangle. So we will directly take this 30 kilonewton plus the point load, that is 15 kilonewton. Okay. So RA plus RB is equals to 45. Next, we know also that summation of movement is equal to 0. From left side, if we calculate at point, okay, at point A. So we will have RB into the total distance, that is 6 meter, and we will have 15 multiply with what? Here the distance is 5 meter plus these 30 kilonewton will be applied at the center of the triangle. You can see this part will be 1 by 3 into 3 and here this part will be 2.2 by 3 into 3. So this 30 will be multiplied with 2 by 3 into 3 plus 1 plus this 1 meter. Okay. So now RB will be 75 plus 40 into 3, that is 90 divided by 6. By 6. Here we will have RB as 27.5 kilonewton into meter. Sorry, kilonewton. RB is also our reaction forces. So here RB is 27.5. We know that RA plus RB is 45. So RA will be 45 minus 27.5. So it will be 17.5 kilonewton. So in this whole numerical we have got our reaction forces. Here RA is 17.5 kilonewton and RB is 27.5 kilonewton. Okay. Now our work is to find out the shear forces. So let's go for the calculation of shear force. So shear force at A will be similar to the reaction force at A. Here we have 17.5 kilonewton. So it will be minus 17.5 kilonewton. Next, we will have shear force at C. Okay. So this shear force at C, how to find out? Okay. Let's take this as CDE triangle. Okay. So here you can see we have cut this triangle into XX axis. Okay. This is our the small triangle. Let's name it as CXF. So here we have two triangles. But as I have already told you that the load is here 30 kilonewton. So this 30 kilonewton is what? Half into the distance, that is 3, multiply with the load here. This is our W. So what is this W? Let's find out. So W will be what? 30 into 2 by 3. W is equals to 20 kilonewton. Okay. So this W is the height between D and E. Right? Now we will find out this. Here let's take this distance as small x and we will find out this small W. So how to find out? Let's use the symmetric triangle rule. So we will have W by 3 is equals to small w by x. This W is 20. 20 by 3 is equals to W by x. So we will have small w as 20x by 3. Okay. So this small w is going to be 20x by 3. Here. So, see, while we will find out this shear force at this distance, what we will get? Shear force at C will be 17 minus 17.5 multiply with 1, and that is same minus 17.5 kilonewton. Let's find out shear force at distance x. So it will be minus 17.5 whole into 1. Here the load will be half into x into what? 20x by 3. That will be applied into distance of x by 3. So, plus 10x square by 3 will be our distance shear force at x. Now, shear force at D. Okay. This will be what? Half into x into the height, that is 20x by 3, 10, yes, 10x square by 3. Okay. So now, okay, if we have the shear force at x is equal to 0, so that we can find out the x value, right? So let's do that. Let's put SF at x is equals to 0. So it will be minus 17.5 plus 10 by 3 into x square as 0. 17.5 is equals to by 3. Now 17.5 multiply with 3 into 10 is equals to x square. So it will be 17.5 into 3, that is 52.5 by 10. root over of 5.25. That is 2.29. So here we have x as 2.29. You can see here this distance we got as 2.29 meter. So these distance will be 3 minus 2.29. Okay, there will be no change. Now we do have the x value here. So now shear force at D will be, this is your shear force at x. So now shear force at D. So you can see if we just put x as 3 in case of shear force at D, so we will find out the value. It will be minus 7.5 plus 10 into 3 square upon 3. So it will be 30 minus 17.5. It will be 12.5. Okay. Now shear force at E. So we do have shear force up to this point. Shear force at E will be R by 15. Okay. So it will be 12.5 plus 15. It will be 12.5 plus 15, that is 27.5 kilonewton. Also, shear force at B will be 27.5 kilonewton, as we already have the reaction force here at RB as 27.5. So now we have the RA and RB values, also calculated the shear force values. Okay. So now let's calculate the bending moment. First thing, bending moment at end support will be 0. So that is bending moment at BA and bending moment at B will be 0. We know that on which point shear force is 0, bending moment will be maximum. So we will find out that. Next, bending moment at C. It is going to be the reaction forces, that is RA multiply with 1. Here, RA multiply with 1, we will have bending moment at C. RA is 17.5 into 1, that is 17.5 kilonewton into meter. Okay. Now, maximum bending moment or bending moment at X. So, it will be 17.5 multiply with the distance X and this point here. We will find out this load, that is we already got it from here. This 10 x square by 3. 10x square by 3 will be multiplied with what? Multiply with the distance. Here, you can see as we are finding out here at this point. So, it will be multiplied with x by 3 distance. Right? So, now we can put the values of x and can find out the maximum bending moment. This 17.5 multiply with x is 2.29 plus 10 into 2.29 whole cube divided by 9. Now it will be 17.5 into 2.29, that is 40.075 plus 2.29 into 2.29 to 29, 12 into 10, 13.33. 13.33. Now the maximum bending moment will be 53.405. 53.405 kilonewton. It will be kilonewton into meter. It will be our maximum bending moment. Also you can see. Okay. Next is bending moment at D. So bending moment at D will be 17.5 multiply with what? Multiply with the distance, that is, here you can see this will be multiplied with the whole distance, that is 3 plus 1, that is 4 meter, and it will be multiplied with this much of distance, that is 3 meter minus 2.29 meter. And here if you put the values like 10 into 3 square upon 3 will be multiplied by 3 minus 2.29. 17.5 will be multiplied with 4 plus. These calculations are little bit complicated. You need to find the values properly or else the answers will be wrong. Plus 3 minus 2.29, that is 0.71 will be multiplied with 30. That is 21.3. It will be your minus. So 70 minus 21.3, that is 48.7 kilonewton into meter. Now bending moment at E. Here we can also calculate, like we have 27.5 here. We can multiply this distance and can find out. It will be easy for us. Like 27.5 into 1, that is what? 27.5 kilonewton into meter. Right? So here we all have the shear force and bending moment values. Now we can draw the SFD and BMD. Always we need to remember that the first thing, in case of SFD, there will be always change of sign. But in case of bending moment, there will be less change of sign. First, shear force. Here we will have 17.5, that is in negative. We will have here minus 17.5. Here, this one. And shear force at C will be same, that is minus 17.5. Okay. Let's, we will show at every point the shear force diagrams. Okay. So here also we will have minus 17.5. Shear force at X is, oh, we have not find out that value. Let's find out here. That is minus 17.5 will be multiplied with 1, that is, so plus 10 into 2.29 square divided by 3. It will be 52.4 divided by 3, 17.46. So here shear force at X will be 17.46 kilonewton. Zero, and this is your what? 12.5. Here we will have 12.5. Next value is 27.5 at both the distances. Okay. Here 27.5 and here also 27.5. Okay. So this diagram will be linear. Also this will be linear, but in case of UVL it will parabolic. Okay. This will be like join this line in linear shape. So this part represents the SFD diagram here. Okay. Next work is to draw the BMD. We know that end supports BMD will be 0, 0. Here also 0. This is 17.5. Next 53.40. So here we will have 17.5. Here we will have the maximum bending moment, that is 53.40, and here we will have the 48.2 something, and this will be 27.5. So this bending moment diagram will be look like this. Here this bending moment diagram represents the numerical here. If you use proper shape, it will be proper positive curve here, and you can see this is your linear structures, and while application of UVL is there, we will have parabolic structure here. Okay, so here we have solved the numerical. We will solve lots of numerical in our next classes. Thank you so much.